Okay, find the Maclaurin series for 1 plus x to the k. Well, I'm going to do what I normally do, start taking derivatives. The 0th derivative of x is going to be 1 plus x to the k. And I'm going to evaluate that at x equals 0 because it's a Maclaurin series, which will give me 1 to the k, which is just 1. The first derivative will be k times 1 plus x to the k minus 1 evaluated at x equals 0, which is just going to be k times 1 raised to the k minus 1, which is just k times 1, or k. The second derivative is going to be k times k minus 1 times 1 plus x to the k minus 2 evaluated at x equals 0, which is going to be k times k minus 1. And I think I can see a pattern developing here. The nth derivative is going to be x, of x, is going to be k times k minus 1 on out to times k minus n plus 1 times 1 plus x to the k minus n evaluated at x equals 0, which is k times k minus 1 on out to k minus n plus 1. Now, if you wonder where this k minus n plus 1 comes from, look up here. N is 2 in this case. So k minus 2 plus 1 is k minus 1, which is right there. Here, n is 1. So k minus 1 plus 1 is just k, which is what we had right there. So it makes sense that the nth derivative is going to give me this k minus n plus 1 more. So now I can use this to put together Maclaurin series. So we have 1 plus x raised to the k is going to be equal to, see, this is going to be the sum, n equals 0 to infinity of k times k minus 1 on out to k minus n plus 1 times Maclaurin series x to the n over n factorial. Now, this value right here, we actually refer to this as being the binomial coefficient. And I'm going to rewrite that. And I'm going to suggest that this value is actually equal to k factorial over n factorial times k minus n factorial. And to show you that's actually legitimate, let's expand this out. This is going to be k times k minus 1. And so keep right on going. And then at some point I'm going to have k minus n plus 1. And then k minus n. Then k minus n minus 1. K minus n minus 2. And so forth until I get down to 1. On the bottom, I have n factorial, which I'm just going to leave there. Then k minus n factorial. Well, that's k minus n times k minus n minus 1 times k minus n minus 2, all the way down to when I get to 1. Now, if you look at these, all of these are going to cancel. K minus n minus 2 right there. K minus n minus 1 right there. K minus n right there, and that leaves me with exactly what I started with. So this is like a shortcut to represent all that other stuff. And actually we have another shortcut notation-wise. We say that k factorial over n factorial times k minus n factorial is equal to k choose n. That's not a fraction, it's a k over n without the fraction bar inside parens, and we say it's k choose n. It's very commonly used in combinatorics to say, hey, I have a group of k, how many ways can I take n out of them? That's one notation that you commonly see in statistics. So with all of this, what I can show is that the binomial, or this is actually called the binomial series, and I can represent this as 1 plus x to the k equals a sum n equals 0 to infinity of k choose n times x to the n, and for x less than 1. Well, that's true, but to show that's true, let's go ahead and do what we always do. Take a look at the limit as n goes to infinity of absolute value, so I'm going to have k times k minus 1 on out to k minus n plus 1 plus 1, x to the n plus 1 over n plus 1 factorial times n factorial over k times k minus 1 on out to k minus n plus 1. So I'm going to rearrange these as, oops, I've got my x to the n. I need an x to the n right there. So this equals a limit as n goes to infinity. Let's put my factorials and everything all over top of each other. See k minus 1 on out to, see, I'm going to give myself just a little bit of room here. K minus, actually it's k minus n, because this is k minus n minus 1 plus 1, so that's just k minus n. And then I have this other factorial, so I have k times k minus 1 times k minus n plus 1. Now notice right here would be a k minus n plus 1. That's the term prior to k minus n. See, that's going to be times x to the n over, x to the n plus 1 over x to the n times, see, n factorial over n plus 1 factorial. So there's all my terms rewritten, so everything's stacked up, so make it a little bit easier to see what I'm going to do in terms of cancellation. Well, clearly these k's cancel all the way down to k minus n plus 1, which leaves me a k minus n in the numerator. This will cancel, just simply give me x. The n factorial will cancel to give me simply n plus 1 in the denominator. So this is actually equal to the limit as n goes to infinity of, what did I end up with here? Absolute value of k minus n over n plus 1 times, am I missing anything? Just my x. Well, that I'm going to rewrite as the limit as n goes to infinity, absolute value of k over n plus 1 minus n over n plus 1, and all of that is times x. Well, in the limit, this will go to 0, this will go to 1, so I have a negative 1. So this is actually equal to the limit as n goes to infinity, absolute value of negative x, which is just the absolute value of negative x, which is just x. So I need this to be less than 1, so what I really need is the absolute value of x to be less than 1. Okay? So that is what justifies that statement right there.